Dear students, welcome again. In the last class on the series, we are seeing all the 5 forms of comparison test. Just recall those. In this session, we shall see the P series. It is also called as harmonic series. Let us see first how the P series looks like. The series sigma 1 by n power p, n runs from 1 to infinity, which is equal to 1 by 1 power p plus 1 by 2 power p plus etc. plus 1 by n power p plus so on is called the P series or harmonic series. The series of this form is called P series or harmonic series. Let us see how the P series behaves. See the theorem. The P series sigma 1 by n power p is convergent if p greater than 1 and divergent if p less than or equal to 1. That is, the P series converges if p greater than 1 and diverges if p less than or equal to 1. Let us see the proof. Case 1. When p is greater than 1. Consider the P series. I have written the P series in this form. That is 1 by 1 over P, 1 power P plus 1 by 2 power P plus 1 by 3 power P. Make this as one group plus 1 by 4 power P plus up to 1 by 7 power P. Make this as another group plus 1 by 8 power P plus up to 1 by 15 power P. Make this as one group. This is sum of 2 terms. This group is sum of 4 terms. Your sum of 8 terms. Similarly, in next group we will be having sum of 16 elements and so on. Okay, write the P series in this form first. Now, concentrating on this group first. See, since 3 power p is greater than 2 power p, this implies 1 by 3 power p is less than 1 by 2 power p. Adding 1 by 2 power p to both sides of this inequality, we get this inequality. 1 by 2 power p plus 1 by 3 power p is less than 1 by 2 power p plus 1 by 2 power p. This sum is nothing but 2 by 2 power p, that is 2 times 1 by 2 power p, and this can be written as taking 2 to denominator. This is nothing but 1 by 2 power p minus 1. See, similarly, concentrate on this group. This sum can be written as 1 by 4 power p plus 1 by 5 power p plus 1 by 6 power p plus 1 by 7 power p is less than 1 by 4 power p plus 1 by 4 power p plus 1 by 4 power p plus 1 by 4 power p, which is nothing but 4 times 1 by 4 power p, and simplifying we get 1 by 4 power p minus 1. Writing 4 as 2 square, this can be written as 1 by 2 power p minus 1 whole square. Okay. Similarly, 1 by 8 power p plus etc. plus 1 by 15 power p is less than 1 by 2 power p minus 1 whole cube, and so on. With this, equation 1 can be written as sigma 1 by n power p, which is nothing but this sum, right, is less than 1 plus this is less than 1 by 2 power p minus 1 plus this sum is less than 1 by 2 power p minus 1 whole square plus this sum is less than 1 by 2 power p minus 1 whole cube plus so on, right? Now, clearly, you can see that the series in the RHS is nothing but geometric series, right? This is a geometric series, and here you can see that the common ratio is 1 over 2 power p minus 1. And since p is greater than 1, p minus 1 is greater than 0, and so 1 by 2 power p minus 1 is obviously less than 1. So the series in RHS is a geometric series with common ratio less than 1. We know that if R is less than 1, the geometric series is convergent. Okay, so the series in RHS is now convergent. Now applying first comparison test. According to the first comparison test, sigma 1 by n power p is also convergent. This is when p greater than 1. So when p greater than 1, the p series converges. Let us see the remaining cases. Case 2, when p is equal to 1. When p is equal to 1, the p series becomes sigma 1 by n is equal to 1 plus 1 by 2 plus 1 by 3 plus etc plus 1 by n plus etc. See here, sum of first two terms keep as it is. Next, going to these two terms. See, since 3 is greater than, 3 is less than 4, 1 by 3 is greater than 1 by 4. 1 by 3 is greater than 1 by 4. Add 1 by 4 to both the sides of the inequality. We get this inequality. 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. Now, sum in the RHS is nothing but 2 times 1 by 4 and it is 1 by 2. Next, consider the sum of next 4 terms from starting from 1 by 5 to up to 1 by 8. 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. See here, continue the same argument. 7 is less than 8, so 1 by 7 is greater than 1 by 8. 6 is less than 8, so 1 by 6 is greater than 1 by 8. 5 is less than 8, so 1 by 5 is greater than 1 by 8. Add 1 by 8 to both sides, we get 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is greater than 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. And this sum is nothing but 4 times 1 by 8, and after simplification, we get 1 by 2 and so on. Continue the same process. Then the p series with p is equal to 1 can be written as sigma 1 by n is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus etc, which is greater than 1 plus this sum is greater than 1 by 2 plus next sum is greater than 1 by 2 that we have shown here plus 1 by 2 plus etc. See, clearly the series in the RHS is divergent. Now, by second comparison test, sigma 1 by n power p is also divergent. This is when p is equal to 1. Let us see the last case, that is when p less than 1. When p less than 1, n power p is less than n. This implies 1 by n power p is greater than 1 by n. See, here there is a small correction. Please do make this. This is not less than, this is actually greater than. N power p less than n implies if we take the reciprocal of this, we get this, that is 1 by n power p is greater than, please do make the correction, 1 by n power p is greater than, I am repeating, 1 by n power p is greater than 1 by n for all the values of n. But we know that sigma 1 by n is divergent. This is by case 2. Right now we have proved that when p is equal to 1, sigma 1 by n is divergent. So in the series in the RHS is divergent. Now by second comparison test, sigma 1 by n power p is also divergent. This is when p less than 1. So the conclusion is the the p series sigma 1 by n power p is convergent if p greater than 1 and divergent if p less than or equal to 1. So this is how the p series behaves. Let us see one small note. Just recall the third comparison test. What we seen there in the third comparison test, we have seen that limit n tends to infinity, an by bn is not equal to 0. Let us see what happens if this limit is 0. Suppose that this limit is 0. Then sigma an and sigma bn do not both behaves alike. That is, in such a case, sigma bn converges. If sigma bn converges, then sigma n converges. But if sigma bn diverges, then it is not necessary that sigma an is also divergent. Let us see. Let us see the first case. Let us see the convergence first. Suppose that limit an by bn is equal to 0 and sigma bn is convergent. Then here we are showing that sigma n is also convergent. It is given that limit an by bn is equal to 0. Now by definition of limit, for given epsilon greater than 0, there exists a small m such that modulus of an by bn minus 0 is less than epsilon for all n greater than or equal to m. This is by definition of limit. Now by property of modulus, this inequality can be written like this. That is, an by bn is greater than minus epsilon and is less than epsilon for all n greater than or equal to m. Now considering this part, that is our right portion, we get an is less than epsilon times bn for all n greater than or equal to m. Since sigma bn is convergent, by first comparison test, sigma an is also convergent, right? So this is about convergence. Let us see the divergence part. Suppose that limit an by bn is equal to 0 and sigma bn is divergent. But here sigma an is not divergent. That is, sigma bn is divergent doesn't imply sigma an is also divergent when limit an by bn is equal to 0. Let us see this in one example. Consider the two series. One I have taken it as sigma an. Let sigma n is equal to sigma 1 by n cube, and another one is sigma bn is equal to sigma 1 by root n. Both are p series. Clearly you can see that both are p series. In sigma an, that is in sigma 1 by n cube, value of p is 3. It is clearly greater than 1. And right now we have see how the p series behaves. According to that, in this case, the p series is convergent. But here you can see that the value of p is 1 by 2 and it is less than 1. And so it is divergent. This is divergent, but whereas sigma an is convergent. But you see here, limit of an by bn is 0 here. Limit an by bn is nothing but limit an is 1 by n cube, bn is 1 by n power 1 by 2. By simplifying, we get 1 by n power 5 by 2. Applying limit to this as n goes to infinity, we get 0. But we have seen that sigma bn is divergent, sigma n is convergent. So if limit an by bn is equal to 0, then sigma bn is divergent doesn't imply sigma an is also divergent. It is not necessary. Okay, dear students, let us see in the next session.